this last property, it's not exactly there. And so just as an example, let's consider 2 qubits on this processor, so in the blue and green circles. And let's just look at the evolution of these two. So actually they correspond to blocks here in this case. So just assume for now that they are decoupled qubits, and we just look at what happened after time t. So of course they just follow some Larmor procession. And here, to simplify things, what you did is that in the first qubit, so the blue one, we fix it in its z.2 state, so plus z minus z. And the second qubit, we fix it at plus state. So what happens is, of course, the second qubits oscillate in the xy plane with some angle given by its resonance frequency times time. Now that is fine. Now let's just add some new terms. So a ZZ term. I'll explain in a bit why. Now what happens is depending on the first qubit z-pointer states, the angle in the xy plane is now going to change. And so, for instance, here, if the first qubit in the plus z state, it's going to oscillate faster than the other case. And so this is really a dephasing error. Now, the reason why I added these ZZ terms is because actually all of resonant interactions that happen between these, the 2 qubits due to some capacitive coupling, for instance, in the processor, will generate such a term effectively. And so that's why I've been considering this. The thing is that this dephasing error arises in entangled states, so in the Bell states, and it doesn't commute with transverse gates, so I mean X, Y, C0, and even swap gates. So it has some entangling power when mixed with transverse operations. And really, this decreases the simulation fidelity. Also, it cannot be corrected with single qubit gates. It can, however, be corrected with proper driving schemes, echo measurements, and so on. But more importantly, it can be reduced with better circuit design. And that is the subject of this talk. So let's just let me give you an example of why this arises. And so let's just consider, for instance, 2 transmons here. So you've seen this a couple of times already from Alexandre's group. And so a transmon qubit actually is implemented with, for instance, a squid loop, so 2 Josephson junctions in parallel, also in parallel with a large capacitance. And such a circuit can actually be mapped to a Kerr oscillator. Here A is an annihilation operator, the frequency, and alpha is the anormality in this case. So it basically tells you by how much the second level is pushed from the the standard oscillator spectrum. And now let's just add some capacitive link between the two, so you have single excitation exchange between the qubits. And now we can look at the spectrum again at low energy states. And what happens is that there is an off resonant exchange between the 1,0 and 0,1 state, and similarly between the 2,0, 1,1, and 0,2 states. So here the first index is associated with the level of the first qubit, the second with the second qubit. And because of the energy uncertainty principle, you can go to energetically forbidden states for a small amount of time, given essentially by 1 over the energy gap. And this is translated basically as the Fermi Rule. And you can basically compute energy shifts associated with all of these virtual transitions, but we can stop at the lowest order. And for instance, the 0,1 state is going to be pushed by G squared. So G again is the coupling rate here over the between the 2 qubits delta. And you can do this for the 1,0 state, but similarly for the 1,1 state. And in the 1,1 state, you have shifts coming from both the 0,2 and 2,0 states. And in this case, it's going to be also renormalized by the anormality, so delta minus the anormality, for instance, of the second qubit, and minus alpha 1 for the first qubit. You still see my pointer, imagine, right? Okay.
Wait, ça marche.
Yeah, we do.
Okay. And so essentially, the ZZ error I mentioned earlier, it's related to the renormalization of the 1,1 state. And so assuming small anormalities, you right away extract the ZZ rate as being associated with the sum of the anormalities in the 2 qubits. Of course, renormalized by G over delta squared. So you see that if the anormalities are strong, this actually is a strong quantity. Now, the point is, we can consider other types of qubits. So let's, for instance, consider the case where the transmon is now going to interact with another type, the generalized flux qubit. So it's a slightly more complicated circuit. And we have a small junction in parallel with a large junction array, sorry. And you can also have some external flux bias to change the properties of the spectrum. And in a specific parameter regime, we'll come back to this in a bit, you can have also a K oscillator, but this time have a positive anormality instead of -1. And you can do the same process as before, so add a capacitive link and compute all the energy shifts, and now you can find the ZZ rate, and of course it's still related to the sum of anormalities, but since one has a negative sign and the other has a positive sign, if they both have a similar magnitude, you can see that the ZZ is now going to be suppressed even if you have large coupling. Of course, it's going to have some renormalization of the anormalities due to the circuit properties and so on, but this tells you that there is a sweet spot where this could happen. And there's also higher order processes, of course, that induces renormalization of the ZZ. All right, so again, here the problem was that we have this ZZ crosstalk we mentioned earlier. It's there in all kind of superior dating circuits, and it really limits the gate fidelity. It's really an always-on interaction, so we really need to decrease it. And normally, to be able to decrease it to below some tolerance value, we need a very weak coupling, which is a problem because to have fast gates, fast 2-qubit gates, we need a stronger coupling. And the reason we need faster gates, of course, is because we are coherence limited in our simulations. The ZZ interaction can also be long range in your processor, so it's not just a nearest neighbor thing. So the solution we have here is to implement a new type of qubit. So, the GFQ I mentioned earlier, but in a specific parameter regime, such that we call it the QMON. And it's really basically an anti-transmon. It looks like a transmon with a positive anormality, but it has almost all the nice properties of a transmon. And also, it's a scalable design, so we basically want to build processors out of this design. All right. And so there are different requirements here. But essentially, the bottom line is that we want it to look like a transmon and to have really the same nice properties. So, have a charge dispersion, have weak flux tunability, to also avoid some fine-tuning conditions in our circuits to be able to fabricate this easily. We also want to prevent, the need for fast controls, and we also want to work really at what we call a sweet spot, but essentially we don't want to induce noise in our circuit. And we basically want to really prevent the need to have active schemes to suppress the ZZ. And also, more importantly, is that our design doesn't require like a very hard, like a very strong complexity, doesn't have a lot of complexity. And the goal is really to be able to have really fast gates because we could have stronger coupling with suppressed ZZ. And last thing I should mention, again, is like we said, like the QMON is really like an anti-transmon, so it can be understood with a K oscillator, and that's another advantage because anything you want to implement and design, such as gates, controls, and so on, you can really think with a very intuitive model, and so that's a huge advantage it has over other types of qubits. All right, so the first thing is that the generalized flux qubit in general, it's a multimode circuit. So we're dealing with possibly a large junction array here. And so there's a lot of degrees of freedom. And ultimately what we want is we want it to act like a transmon, so with a single degree of freedom. And so at first this seems a bit difficult. Still, we managed to find a 1D model that captures very well the dynamics of this large object. So at low energies where this junction array basically acts like a single object, we find that there is good agreement. So if you look in panel A, in pink, you have the exact, comes from a numerical dilation, but you have the energy levels coming from exact numerical diagonalization for the full circuit with all the degrees of freedom. And in that, the dashed lines corresponds to our effective 1D model. And you see there is really strong agreement. And this is against the external flux bias in the circuit. And the QMON essentially is operated near alpha quantum flux where the anormality would become positive. But we see there is really strong agreement at low energies. And so since we're dealing with qubits, we mostly want to work with the lowest energies, so 0, 1, the first 3 levels.
Katrina, I'd have a short question. In
Yes.
your panel A, there's a horizontal line around 20. So is that part of the, yeah, this one.
Yeah.
So that part of them, what is that?
Yes. So basically, this is the plasma frequency. So it's associated with, the fact that at low energies, essentially, we assume that we can basically freeze all of the degrees of freedom in the array such that it acts like a single object. But beyond some values, so this value is essentially the frequency, the single junction frequency. At that point, we can no longer do that. We can no longer freeze a junction array.
Okay.
And so that is what this corresponds. So there we do not capture, if you want, the excited states associated with the modes in the array. Our model only captures what happens if this array is frozen, basically.
Sorry, I didn't look carefully enough. It's the omega p is there, yeah.
Sorry, I didn't hear. Sorry.
Yeah, I hadn't looked too carefully enough at the figure because you indicated omega p over 2 pi there. So that's the plasma frequency, yeah.
Yeah. Okay. And then in panel B, actually, you see the anomosity of the Qmon. So again, it's just the difference in energy between the second and first level, minus the the energy between the the ground state and the first level. And so you clearly see that near off-quantum flux, we need to have a strong positive anomosity, and this is where we want to work. I will actually, panel C and D are related to charge dispersion. If we have questions, we can discuss that, but it's actually more, detailed discussion. But still, the point is that we can really capture well with 1D model the dynamics of this circuit. And we need to identify a regime where we basically will define the Qmon. And again, what we want to do is to have an effective K oscillator. And you see in panel A, that the first figure is essentially associated with such a system, so it resembles an oscillator. And this is for the case where the small junction, the ratio of the small junction over, the energy of the large junction is below 1 over n, n being the number of junctions in the array. And so in that regime, we can find a K oscillator model, and that's where we want to work. And so what we do next is that we, for instance, freeze, this ratio at 1 over 2n, roughly. So in our case, this means epsilon equals 0.1. And we will look at what happens against the reduced impedance D0. So this reduced impedance is actually related to 0-point fluctuations in our circuit. And again, like for an oscillator model, we basically want the 0-point fluctuations to be very small, ideally to operate a system. And these 0-point fluctuations are essentially related to the ratio between EC over EJ. So EC being the capacitive energy and EJ associated with this, if you want, the inductive energy. All right. If we do that, we indeed notice that the frequency of the Qmon is basically linear with this impedance, and that's totally normal because as for the transmon, we expect the frequency to go as the geometric mean of EC and EJ, and so this should then be linear with impedance, and that satisfies this. We also see that alpha, like the anomosity of the Qmon, not only is it positive, but it grows, we can have an appreciable anomosity. This is all renormalized with EJ, by the way. However, we notice that to be able to have an anomosity on the order of hundreds of megahertz, we need a very large EJ, EJ being the Josephson energy of the large junction in the array. And so we work in a regime where it's around 70 gigahertz. We can do the same exercise and now inverse the role of Z0 and epsilon. And now we see that for, in what we identify as the Qmon regime for an impedance of around 0.04, how the frequency densities depend on the ratio of the small junction over the large junction. And again, we can identify a regime where the anomosity is quite appreciable, and the frequency is still is also quite appreciable, and so that's the Qmon regime. All right. So are we doing time? Okay. So actually, I'll probably skip this, but the point is, for this slide, it was to mention that again there is a trade-off between having a large coupling and a large ZZ. And so normally what we want to do is suppress the G, like the coupling rate, as much as possible, such that the ZZ is below some tolerance value. But now in our system, we can still have a large G and a small z, so that's the advantage. But what we can do here is look, for instance, at how the ZZ depends on the detuning between the two qubits, between the transmon and the Q-bond, for different values of the coupling. So on the right-hand side, you have for a coupling of 35 megahertz, on the left-hand side of 70 megahertz. And you can see, of course, if the coupling is smaller, the 0-point transition is much smoother, so you need less precision. And so we did that, well, actually, MIT did that experimentally, this experiment. And that's what we observe, actually, is that in our system, so the red line here, we can get a ZZ that is much below 1 megahertz. Whereas for a standard transmon system with similar parameters, you would find a much larger ZZ above 1 megahertz. All right. So another part of this project was to do a much more complete theory to capture, all the realizations of the system, to be able to understand how to operate the gates and so on. And so we really wanted to find a way to predict small ZZ and fast gate parameter regimes, but with as much precision as possible. And so compared to standard approaches, what we did is we really analyzed a full circuit Hamiltonian with all the cosine potential associated with the junctions. We use different, we define optimal basis of operation. So we use time-dependent displacement transformation, Jacobi-Hendry expansions to really understand all the parametric interactions happening in our system. We did Bogey-Above transformation to account for strong coupling effects, since here we want to work with strong coupling. We also use time-dependent Fourier transformation to recapture off-resonant processes that normally were not considered, but finally plays a big role in renormalizing the ZZ. And really, our theory that we did could be applied to other gates and architectures. It really differs from standard approach, where they simply use K-associated models for the qubit, and a dispersive transformation, like a Fourier transformation, that work only in the dispersive limit and misses most of their spectralizations and a lot of time-dependent errors. And anyway, I just wanted to show you the kind of results. So here, for instance, you have the anomalies of the two qubits. So in blue, it's the Q-mon, and in orange is the transmon. And the dash, I know it's a bit difficult to see, but the dash line here is the analytics. And the solid lines are from exact numerical organization. And you see that we captured a very strong normalization of the anomalies for a specific system, whereas in the standard theories, this would be a flat line. Similarly, for the ZZ, with our theory, which is still being refined, we capture a strong normalization of the ZZ, which would have been missed. Otherwise, it will again be a flat line around 0 if we were to use standard theories. So that is good. We also identified a regime of operation in red, which is different from the standard regime of operation in blue for gates. Normally, people work in that regime because, as we will see in a bit, the coupling rates, the gate rates are much stronger there. But it's also a regime where there's a strong normalization of the anomalies and the ZZ, and that is because hybridization is strong. We find that there is a regime where we can still have appreciable gate rates, but also a very much suppressed ZZ, and that is this red region. And so what we did is we analyzed the cross-resonant gate in that regime, and basically this gate is just a CNOT gate, and it's done by putting a drive on the first qubit at the resonance frequency of the second qubit, essentially. And again, we look at the gate rates in these regions, and we find that, of course, this depends on the drive power on this first qubit. But we find that, given strong drive powers, we can still have access to a sufficiently strong gate rates. So just to mention that here the ZX is essentially literally equivalent to a CNOT up to an X rotation. And we also find that in our regime, the ZZ can be suppressed almost close to 0 as compared to the standard regime of operation. You also see the ZZ the theoretical ZZ for a theory transmon design, and you can see that in the standard regime of operation it can be very strong. All right. Here we also looked at the ratio between ZZ over ZX, so basically the ratio between the ZZ error over the gate rate. And again, we can see that in the regime that we identify, actually this error rate is very, very small compared to the standard regime of operation. So that's an indicator that this is a good regime. Of course, this doesn't assume any decoherence for now. All right, so let me just move to this. So the next thing is that we can look at the gate fidelity now. So basically the gate fidelity is related to this error rate I just showed. And what we find is that, of course, we are occurrence limited. So T1, T2 is, of course, the occurrence times of our qubits, which we assume to be the same. And what we find here is that, of course, if we work in the red regime instead of the blue regime, we need stronger drive powers, as we said before. But to be able to reach 99.9% fidelity, we will need very long occurrence time. So right now, we need to optimize circuit parameters such that we can get, better gate fidelities, given the current occurrence times, which are more around 100 microseconds for the current devices. But still, with optimization, we hope to, to improve the fidelity. We also did a more complete numerical study for the current devices that are in the fridge. And essentially, we find that it is possible to improve the gate fidelity here. Despite the current times, we will need single qubit gates, additional single qubit gates. And so there is also, among our next step is to improve this fidelity. And also try to fit the experimental results better. There are still some discrepancies. And yeah, I'll stop there for now. Okay. So if you have questions. Hello?
Merci, Catherine.
Okay. I can see the...
Are there questions for Catherine? Question for Catherine?
Yeah, I have one, Alexandre. It's Yves. So what you're proposing is, well, a new architecture that couples a transmon and a QMon. But what if do you need in such an architecture also interactions between QMons, like QMon interactions, and transmon interactions, or you can do away with that because it's just, yeah, I mean, you need some. I have a hard time seeing how you could integrate that in a quantum computer with several qubits.
Actually, you can imagine by having like two lattices, so a lattice of transmons and a lattice of qmons, and interleaving them, and it's really just capacity coupling them. The way of saying this, maybe actually I have an image of a process here. What you could imagine, for instance, if you still see my pointer, is like, for instance, this could be a transmon, this would be a qmon, this is a transmon, and so on. So you never have the same type qubit connected to each other as nearest neighbors.
Okay, but like ideally you'd like to have all-to-all connectivity, no? So there would be sometimes where there would be some coupling between two transmons or two qmons. So
this actually, it's a very interesting topic. So there are pros and cons of having all-to-all connectivity, but with our current devices, I would say there are mostly cons. It's better to have, there is a trade-off. You want sufficient connectivity, but you have to do it in a smart way because there are a few problems that arise from having all-to-all connectivity. There is, of course, frequency collisions. There is, the fact that if you drive one qubit, there is still crosstalk, and you're going to, induce possibly transitions in other qubits. So there's no screening by having all-to-all connectivity. And of course, again, if you don't have proper circuit design, you can have strong ZZ crosstalk. And this is depending on how strong your coupling is. If especially you decide to have all-to-all connectivity and strong coupling, you can have strong hybridization and randomization. And so it's not a good thing. So normally you will have to define a unit cell which you would define as being optimal in the sense that you numerically diagonalize, there's no frequency collision, you can operate, you can do gates and so on, and you replicate this unit cell in your processor. And what we suggest is basically to do such a unit cell when all nearest neighbors would be of different types.
Okay. Okay. So maybe I have a more general question. So has the field abandoned the all-to-all connectivity now, or is it or is still pursued?
So I wouldn't say abandon, but I would say it depends a lot of what type of architectures you're considering or not. In the case of superconducting circuits, depending on how you implement your couplings, if you decide to go, for instance, with capacitive couplings, I would say that doing all-to-all connectivity is not only difficult from the point of view of fabrication, but it also has a lot of difficulties because it's really, it's an infinite dimensional object as well.
Mm-hmm.
So actually, depending on, of course, how you decide to do unit cells and so on, it's still possible to do, basically gates between, two distant qubits using, for instance, an intermediate qubit, so like virtual gate, if you want. So there are possibilities without having direct connectivity. There's also the possibility of using a coupler and connecting or a bus, if you want, and connecting multiple qubits through it and do parametric interactions between pairs of qubits. So there are very different approaches, but having all-to-all connectivity is an extremely, it's more difficult to do anyway. So for superconducting circuits, I'd say it's not the most pursued.
Okay. Thank you. Thank you very much.
Any more questions? So maybe to add to, I think Catherine, you answered perfectly the Yves' question. Of course, but maybe I can mention that one avenue which is now studied a little bit is to have modular architectures, right? To break away even more from this all-to-all, where you would have small processors with just the maximum number of qubits you can think of error correcting, and then you would connect these modules through some quantum links, and so that also removes this idea of all-to-all connectivity.
Okay. Yeah.
For all the reasons that Catherine explained.
Yeah. Very clear answer, Catherine, by the way.
There is also another thing that we didn't mention, but actually there's even the option, like let's say you manage to do very high fidelity and fast qubit gates, and you minimize the errors on it because like you decide to not go with all-to-all connectivity, you can still show in some cases that doing like, let's say, two subsequent 2-qubit gates would be better than trying to have all-to-all connectivity and do this gate. So there is a trade-off between, the connectivity and how you do like the gate scheduling schemes. So anyway, it's actually an active field of research.
Yeah, sorry, I keep interrupting you. More questions or one last question for Catherine? No. So thank you, Catherine. Thank you for your patience. So this is the second time you tried to give the talk. So last time we canceled for lack of attendance. So thank you for giving the talk this time. So there's, as far as I understand, Simon, there is no second talk today, right?
Yeah. Juan sent us an email this morning saying he couldn't attend. So yeah, there's no other presentation because of that. Yeah.
Okay, but it's Yves speaking, but we had the chance to have a very good presentation. So I would say thanks again, Catherine. It's very interesting.
Thank you. It's nice.
Yeah, thanks a lot for the great presentation, Catherine.
Okay.
All right, so
see you next week.
Yeah.
Okay, bye-bye, everyone.
Bye.
Thank you. Goodbye.
Yeah, thanks.
Thanks.
À la
Goodbye.
Merci, Kat. Salut.
D'accord. D'accord. D'accord.